Thank you very much for the kind introduction, and thank you for your attention. My name is Ivana Krajnovic, and as Maria said, I'm a PhD researcher of the Marie project, and I'm doing research in alkali-activated materials used for strengthening and repair at the Manuel van de Vete laboratory. And today I will share with you findings from my internship at the Corning research facility in Chambéry, France, where I worked on the bond between FRPs and alkali-activated materials. So first I will talk a little bit about alkali-activated materials, then I will talk about the inspiration for the bond test with fiber-reinforced polymer and near surface mounted. Then I will shortly introduce materials and test results. So here we have the traditional concrete that is normally made with cement and supplementary cemented materials, blended with water and aggregates to produce concrete. And we have alkali-activated concrete made mainly with supplementary cementitious materials, blended with industrial byproducts and waste, activated with alkaline solutions, and blended with aggregate to create alkali-activated concrete. Why do we do this? Because by omitting cement, we decrease carbon footprint of the concrete, and by using byproducts and waste, we decrease the consumption of raw materials and increase the price of the raw materials. And when we use locally available byproducts, we can reduce transportation costs. So we do this to get equivalent or better concrete performance than PC concrete, and we also use this to invoke curiosity of the public, mainly due to the usage of waste in concrete, and this concrete fits into the circular economy and also helps compensation of construction and so my current mix design for the supplementary cementitious material, I used blast furnace slag, which is locally available in Ghent. We used glass waste powder from glass fiber production from Owens Corning company. We activated it with a mixture of sodium silicate and potassium hydroxide to create, and with sand to create two-component system, alkali-activating mortar. This mix design is in detail presented in our recent publication. Here you can see mix designs for the concrete substrate for a near surface mounted application, then the PC mortar that we use for comparison reasons, and alkali-activated mortar that we use for main research. So here you can see that compressive strength and development between PC mortar and alkali-activated mortar follow similar terms. Same can be said for flexural strength for 170.8. We wanted to test the suitability of alkali-activated materials in structural application with FRP bars, and for that we used two matrix types, Portland cement and AAMs, two fiber types, glass and carbon fiber types, and to measured length in direct pull-out tests. For NSM application, we wanted to check potential for replacement of the cement matched with primary with alkali-activated materials, and there we also use two method types, two fiber types, and two embodiment lengths. We had CFRP bars that are diameter 6 and epoxy impregnated bars with helical wrapping, and for GFRP we had epoxy impregnated sand coated rebars. Mechanical characteristics, I'm sorry I gave in international units. Here you can see the specimen separation. For pull-out specimens, we use polystyrene molds with bond breaker and embedment length of 5 and 10 feet. For near surface mounted, we use also 150 millimeter cubic molds made of polystyrene and wooden pre-nuts for creating the groove. After 1 day with mortar specimens, we roughen the surface of the surface of the groove with a steel brush, and 7 days after the casting, we applied alkali-activated and Portland cement mortars together with the rebars, and we waited for 28 days from the mortar application to test this specimen. So here you can see the test setup. There is the clamp, then the loading frame, and LVDT on the unloaded end of the rebar. The same is for near surface mounting. So we did in total 70 tests with 2 FRP materials, with 2 binding materials, and 2 bond lengths. We did 40 pull-out tests and 30 near surface mounted tests, because in pull-out tests we did GFRP with 6 millimeters with an embedment length of 5 feet for both OPC and AAMs, and for 10 feet the same. And in near surface mount, we omitted 5 feet for Portland cement. We only tested 10 feet. So let's talk about failure mode. For the GFRP, there was abrupt failure with the peel-off of the sand coating with alkali-activated materials, and pull-out without visible damage to the bar for Portland cement. For CFRP, we similarly observed the peel-off of the outer epoxy layer with breaking of the outer fibers. That also created sort of the anchorage in the unloaded end of the rebar, and or pull out of the rebar for Portland cement specimen. Here we can see the average bond stress for the maximum load. We see that the higher stress, we see that the alkali-activated material outperforms Portland cement for more than 50 or 30%. And we see that when changed from 5D to 10D, that in Portland cement mixtures, the average bond stress actually increased marginally, and when it comes to the alkali-activated mortar, it decreases. When it comes to the GFRP, we see also the increase in the bond stress when changed from 5D to 10D, but no increase when changed from 5D to 10D for the alkali-activated. This is the maximum bond stress given by API 441R, and we can see that for 10D, this is a conservative prediction, and this is for the alkali-activated mortar, but for the Portland below curve, which is saying for 5D, and yeah, I cannot claim that, but I think that these higher values are definitely for GFRP, while concrete rebar is CFRP is here. So there is also another line from the research study from Ghent, that they actually investigated FRPs bonded with alkali-activated mortar, and their prediction didn't take into account the position of the bar, and they're actually overestimated our results. So here we can see bond stress versus bond stress behavior. In the upper left corner, you can see GFRP, the alkali-activated mortar for 5D and for 10D. So we see that the behavior is similar, that that on average 5D experience a little higher. And here we can see the comparison of alkali-activated mortar with GFRP for 10D and PC mortar with GFRP for 10D. We see clear increase in the bond stress, but overall behavior is the same. Then here we can see the bond stress split behavior of alkali-activated material for with GFRP for 5D and 10D, and we see the sharp increase in the bond strength and then the stabilization on the maximum bond line for both materials. Similarly, it is for the PC mortar with 10D and alkali-activated mortar with 10D, with a clear difference in the maximum bond stress allowed. So here we can see the bond stress split predictions, where for the alkali-activated mortar and GFRP, the closest approximation was with published in King and Cole in 2015 with a strengthening and downgrading part. The similar is for the PC mortar and GFRP, while for the GFRP and the alkali-activated mortar, actually the CMR model from Constanza et al. In 1995 was proposed, was the best. The same is for PC and GFRP bars. So now I will jump to the failure mode of the new surface mounted stress. We can see here that the failure mode is cracking of the mortar with the fracture of the concrete and peel off of the sand protein sometimes for GFRP with alkali-activated mortar, and cracking of the mortar and fracture of the concrete without damage to the rebar for GFRP. There is a different failure mode observed in Portland cement matrix, where for GFRP there was a mortar concrete interface on the both sides, and for GFRP there was also on the mortar concrete interface with horizontal cracks in one. Contrary to what is found for pull-out tests, here from 5D to 10D, the average bond stress at maximum load increases for about 50%, and for Portland cement, this is for alkali-activated materials, and this is for Portland cement, where we see that in Portland cement with 10D is develops less stress than AAM. When it comes to carbon fiber, there is actually not a lot of fluctuation. So the Portland cement 10D and the alkali-activated 10D are similar, and alkali-activated with 5D develops slightly higher other concepts. And here we can see the curve from ACI for 41R, where with the different C for the different bar position, and we see that all the results are over the curve. Here we can see the bond stress versus slip behavior, this time only for the GFRP with 10D and GFRP with 2C for 10D. We see that the behavior is similar to pull-out tests, and we don't have the 5D bond stress curve because our avidity was destroyed. And for carbon fiber, we see the occurrence, the increase in the bond stress, and for the small levels of stress, and then reaching the maximum and decreasing to the certain point, and then continuing straight for both alkali-activated materials and for Portland cement materials. So here again the bond stress slip prediction behavior was the best in best corrosion in 2015, and for carbon fibers with alkali-activated materials and with Portland cement, we had the best correlation with modified DC models proposed by Consensus in 1997. So in the recap, this study proves a possible combination of alkali-activated mortars and FRPs for both structural and new surface mounted applications. The AAMs outperformed CC in almost all cases. The prediction equations for maximum bond stress and for stress-less behavior found in literature are in good agreement with obtained results, and more research is needed with different bar diameter and with epoxy resin as NSM bonding agent for comparison with AAM. Here are the references from this presentation, and that would be all from me. I will welcome your questions.